Here is the solutions video to the FP3 mock. Here's question 1. To begin with, we should check that we have read the question, and interestingly in this question it asks you to write the arguments between 0 and 2 pi rather than the traditional pi and minus pi. So let's begin. If we write z to the 5 is equal to 1, you might change this to be e to the 2 pi I, since that's the value of 1 in as exponential form perhaps. Then if we take the fifth root, we divide the argument by 5, giving us e to the 2 pi I over 5. We should know that we can then rotate by 2 pi over 5 to get all the other roots. So we get e to the 4 pi over 5, e to the 6 pi over 5, and e to the 8 pi over 5. And finally e to the 10 pi over 5, which is the same as e to the 2 pi I, which is just 1. So we could rewrite that as 1. And indeed we should, because the question says only write non-real numbers in this form. Real numbers should be written in the real number form. Traditionally we would have written these as 1, e to the 2 pi I over 5, e to the minus 2 pi over 5, e to the 4 pi over 5, e to the negative 4 pi over 5. But in this question we had to make sure we read the question, since it asked for the arguments in this form. Okay? For the next one, we're solving z to the 5 plus 32 equals 0. One way to do this is to write z to the 5 is equal to negative 32, and I'm going to write this as negative 32 e to the 2 pi I, since that's just 1. Now to take the fifth root of two factors, negative 32 and e to the 2 pi I, can take the fifth root of negative 32, which is negative 2, and taking the fifth root of 2 pi I, well, I've already done that above. I've got 5 roots, so we can write them as follows. E minus 2, because it's minus 2 times 1, minus 2 e to the 8 pi over 5, e to the 4 pi over 5, e to the 6 pi over 5. Oh, sorry, the first one is e to the 2 pi over 5. Just looks, it's not very clear. Okay. But in the form we want it in, we want this r value to be positive. The r value is currently negative, so this doesn't work. So you can change negative 2 to be the same as 2 times negative 1. Timesing by negative 1 is the same as timesing by e to the pi I. So we can just change these negative 2's to 2's, but add pi to the argument. So we get 2 pi I over 5 plus 5 pi over 5, which is the same as adding pi, is e to the 7 pi I over 5. This one becomes e to the 9 pi over 5, e to the 11 pi over 5, and e to the 13 pi over 5. The final two are not in the correct form because their arguments are bigger than 2 pi. So if we subtract 2 pi I from the arguments, or 2 pi from the arguments, then we've rotated 360 degrees, so we have the same value. Doing that gives e to the pi I over 5 and e to the 3 pi I over 5. Okay, next we can plot all of these on an Argand diagram. We know that 2 pi I, or 2 pi over 5, is the same as 72 degrees, and we know they're going to be equally spaced 72 degrees apart. So negative 2 has been plotted already, that's on the real line. They all have magnitude 2, so they lie on this circle. Here we have pi I over 5, 36 degrees. Then if we just rotate 72 degrees, we should get a nice pentagon shape if we were to join all the lines up. This one, these 5, and then we just write down what they are. Okay, and then once you've written down what they are, that concludes the question. Question 1, not too bad. Next. Okay, use substitution. This is a classic question. Will probably involve the integrating factor. If we let u equal y squared, then du dx is equal to 2y dy dx. This is implicit differentiation. I'm going to write it as follows. Dy dx is equal to 1 over 2y du dx. I'm going to substitute this in and see what happens. So replacing dy dx by 1 over 2y du dx from the question, and then replacing, well actually I'm not going to replace y yet, I'm just going to write it as minus 2y, then e to the x over y. If I times through by 2y now, I get the following. du dx minus 4y squared equals 2e to the x. But this makes it easier because I can just write y squared is u, giving you du dx minus 4u equals 2e to the x. Okay. A nice symbol notation there saying I can do this because of star, or by dagger in this case. Next, we're going to find the integrating factor, which is e to the px dx. Px in this case is just negative 4, so the integrating factor is e to the negative 4x. Timesing through by e to the negative 4x gives you e to the negative 4x du dx minus e minus 4 e to the negative 4x u equals 2 e to the negative 3x. These two terms, when you integrate them, this came from differentiation of a product. So integrating gives you u e to the negative 4x. You can check that if you were to differentiate u e to the negative 4x using implicit differentiation, you get the line above. So the right-hand side, then we just need to integrate this. Integrating the right-hand side gives us minus 2/3 e to the minus 3x plus c. Our goal is now to make, or we could put y back in, and then divide through by, or times through by e to the 4x to give us the following. And then square root to get y on its own. And this is the final answer. Let's just go back. So y is equal to square root negative 2/3 e to the x plus a constant times by e to the 4x. Next question. A very similar question to the previous one. So letting y equal 1 over u, dy dx using implicit differentiation is negative u to the negative 2 du dx. The differential equation, which was 2 over y minus x over y squared dy dx equals 1 over x squared, replacing 2 over y by 2u, then negative x over y squared by negative x u squared times by negative u to the negative 2 du dx. Finally, this is equal to 1 over x squared. The u to the squared cancels with the u to the negative 2. So this becomes 2u plus x du dx equals 1 over x squared, which is what we were asked to show. Okay, use this to find y in terms of x. So let's find an integrating factor in a moment. Rewriting the question. Well, to find an integrating factor first, we need to have du dx on its own. So if we divide through by x, we get the following. Integrating factor is going to be the integral, or e to the integral of 2 over x dx, which is going to be e to the 2 ln x, which is e to the ln x squared, which is x squared. So our integrating factor is x squared. Timesing through by x squared gives x squared du dx plus 2xu equals 1 over x. Now the integral of the left-hand side is going to be x squared u. Check that by differentiating x squared u using the product rule, and then integrating 1 over x gives you ln x plus c. Dividing through by x squared gives you 1 over x squared ln x plus c over x squared, or factorising gives you 1 over x squared brackets ln x plus c. Then replacing u by 1 over y and taking the reciprocal of the right hand side to get y on its own will give you y is equal to x squared over ln x plus c. May have taken a few more lines to do that, but that should be the value of y. The only thing left to do is to substitute in the limits to find the value of c. Doing this gives us c is equal to 1. So the final answer should be x squared equals ln x plus 1. I think I said that totally wrong. I meant y equals x squared over ln x was ln x plus 1. Okay, let's look at question 4 now. So this is about using multiplication to do spiral enlargements effectively, where the spiral enlargement doesn't really do any enlargement, it's just a rotation. So if we plot the origin, since we're asked to plot the origin, which is O, let's just plot some z, say here, and then timesing by e to the pi I over 6 is going to be a 30-degree rotation about, or anti-clockwise. So this is going to be z e to the pi I over 6, where this argument, or this angle between them, is pi over 6, 30 degrees. This is A and this is B. So that any plot that looked a bit like that would have been sufficient. Okay, part 2. Oh, not quite part 2. We're asked to show that the triangle is isosceles. So when is a triangle isosceles? A triangle is isosceles in this case if OA equals OB. OA is the magnitude of Z, and then OB is the magnitude of Z e to the pi I over 6, which is the same as the magnitude of Z times by the magnitude of e to the pi I over 6. The magnitude of e to the pi over 6 is 1, so this OB is just Z. So we're done. The triangle must be isosceles. Next, let's plot for part 2 1 plus I and 5 plus I and label these C and D. Now E is going to be over here, which is going to be a rotation of 30 degrees from CD, or it could be the other way. Okay, these are possible values for E. So for this, we're going to have to take CD, times it by e to the pi I over 6 to get CE. Okay, or we could times it by negative pi I over 6. So CD is going to be negative OC plus O to D. So to find that vector CD, or that complex number C to D, we're going to do the following. Negative OC plus OD, and then we're going to times it by e to the pi I over 6. OC, when you do this, you get 4 plus I. Check that you agree. Timesing by e to the pi I over 6. Since we're asked to write the final answer as a plus bi, it might be sensible to rewrite this as cos pi I over 6 plus I sine pi over 6, or just use your calculator if it's good enough. This is 4 plus I times by root 3 over 2 plus I over 2. When you do the expansion, you get negative 1 plus 4 root 3 times a half, plus a half I, 4 plus root 3. Okay, so this is C to E. All that's left to do is to find O to E. Now O to E is just going to be O to C plus O to E, which is just adding 1 plus I to C, E. Doing this gives us a half plus 2 root 3 I, plus 2 root 3 plus I times by 3 plus root 3 over 2. Okay. So that should be one of the values for OE. The other value, we can just do the same thing. It's going to be C to D times by root 3 over 2 minus I over 2. Doing the expansion gives you a half plus 2 root 3 plus I times by root 3 over 2 minus 2. Then to find CE, we're going to, or OE rather, we're going to do OC plus CE. This gives us root 3 over 2 plus 2 root 3 plus I times by root 3 over 2 minus 1. So these are the two possible values for OE, the complex number omega in the question. So this is omega. Or W, it's not really an omega, is it? Okay, question 5 then.